DSPT, Disassembly Sequence Planning Transformer for Interaction Guidance in VR. In this paper we propose a novel transformer-based network, Disassembly Sequence Planning Transformer, DSPT, to plan disassembly sequence for virtual disassembly applications. In each time step, our DSPT predicts the disassembly probability of each part, and highlight the parts with the highest probability. User uses this highlight as visual guidance to select and disassemble the parts of the object. Compared to the SOTA method, ASAP DSPT achieves better sequence accuracy and stepwise accuracy in the disassembly sequence planning. Here is an example. With ASAP method, the predicted disassembled parts may be surrounded by other parts and cannot be disassembled during the prediction process. While with our DSPT the predicted disassembly sequence is more consecutive and reasonable, due to the introduction of visibility features and the guidance of the sequence of disassembled parts on the current parts to be disassembled. This is architecture of our disassembly sequence planning transformer, which mainly includes two modules, temporal feature construction and temporal spatial score-based predictor. Our method achieved a sequence accuracy of 60.29% and a stepwise accuracy of 87.68%, which achieves performance improvements in the disassembly sequence planning task compared to the comparison method. The experimental results also show that although the disassembly sequence accuracy and stepwise accuracy tend to decrease as the number of assembled parts increases, both accuracy decreases tend to level off as the number of parts increases. Moreover, our method outperforms the ASAP method in terms of sequence accuracy and stepwise accuracy regardless of the number of parts. Here is a visual comparison between our method and the comparison method for the prediction of disassembled parts for 5 objects. The heuristic volumes method prioritizes the smallest parts, thus predicting the order of parts to be disassembled in order of volume. For example, in the case where a small part is constrained by a large part, the method still predicts that the small part will be disassembled first. The heuristic distance method always prioritizes the parts farthest from the center point. However, not all peripheral parts are prioritized for disassembly. In cases where parts far from the center point are constrained by parts close to the center point, etc., the method still predicts that distant parts are disassembled first. The ASAP method does not consider the effect of visibility on disassembly. As a result, a predicted disassembled part may be surrounded by other parts and cannot be disassembled. In contrast, our DSPT method takes into account the visibility feature and the guiding effect of the disassembly sequence on the current disassembly, so its predicted disassembly sequence is more continuous and reasonable. However, there are some worst cases, e.g. assembly 5, where all methods incorrectly predict a non-removable circle. However, the circle cannot be directly disassembled due to a small raised edge at the front end of the enclosed object. This is a visualization of the temporal spatial score during the disassembly of assembly 2. The y-axis represents the disassembly order and the x-axis represents the part index, organized from left to right according to the disassembly order. At each time step, the part selected for disassembly is usually the part with the higher temporal spatial score for that step. In this disassembly process, part 6, part 10, and part 9 are adjacent to part 5, and they act as fasteners that limit the disassembly of part 5. As these 3 parts are gradually disassembled, we find that the temporal spatial score of part 5 shows a significant upward trend. This is due to the gradual increase of its temporal score, indicating that the feasibility of disassembling this component increases with time. After the removal of component 10, the temporal spatial score of component 7 also shows a significant increase. This is because part 10 is also a fastener that restricts part 7, and once removed, part 7's temporal score rises, leading to an increase in its overall temporal spatial score. We designed a user study to evaluate the efficiency and usability of our method. With ASAP method, when a part is predicted to be removable in the next step, the system highlights the part to give guidance to the user observes and tries to disassemble it and realizes that it is actually not removable. The user needs to independently choose a removable part to disassemble, And then ASAP replans the next part to be disassembled based on the structure of the remaining objects. Our DSPT approach follows the same prediction and guidance process. However, since the stepwise accuracy of our method is higher than that of ASAP, the time to complete the task is significantly reduced. In terms of usability scores, the t-test results show that users rated each metric significantly higher using our method compared to ASAP. This is due to the high prediction accuracy of the entire sequence, which provides a better user experience by reducing user frustration when the prediction fails. Thank you for watching.